Hey everybody, we're going to talk about heat engines and thermodynamic cycles, right? So this is what's called the Otto cycle. Otto, named from Nikolaus Otto, not the same as Auto, although this is what's used in a internal combustion engine in an automobile. So the point is this, right? You have heat input here. Remember that? Isochoric heating here. And you use that high pressure, which is what? That's 3.297 megapascals. That's like 33 ATMs of pressure inside of this piston, right? That has now been pressurized due to this work input. The issue with the work input is that this piston, which is connected to like a crankshaft, right, which turns, right, is losing energy. So the piston loses energy if the gas gains energy. I hope that makes tons of sense. That the piston loses energy when the gas gains energy. Of course, energy is conserved. You can't create energy from nothing. Energy is one of those magic quantities in the universe, right? Coming from the time symmetry of the laws of physics. I don't know if we've talked about that or if we will, depending on when you're watching this video. Either way, we've accepted that energy is conserved so that if something gives it, it takes away from something else. So if the gas is being squished, the piston slows down. So if we want to turn a crankshaft with this piston, right, then putting positive work will slow it down. But then when it comes out at this higher pressure, this is a low pressure compression. We then input heat to blast the pressure, right? You get fire under here. 2,400 Kelvin fire will take the gas to 2,400 Kelvin isotherm. And then you use that pressure to allow the piston to expand upward. And you have a work output. So heat is going in, work is going out. And the work that went in, right? So negative work means that the piston gains energy. So here we have our little diagram again. And the piston is now like, you have this high pressure, 33 ATMs, pushing up, right? These particles are just going crazy fast and they're pushing up on this piston. So therefore, the gas particles are losing energy. We have adiabatic expansion. They're going to cool down to, what is it, 1378.438 Kelvin, right? And they're going to drop in pressure. But where did that energy go? That energy went to moving the piston. So this energy goes into piston. So even though the gas is losing energy, that's work output onto the environment. The environment is this moving piston, which is attached to this crankshaft. So then this crankshaft gets like a pa-chow, boom, 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 right? Right? It starts turning, right? Really fast. So you have all this energy output. Great. And then you need to dump the heat. This is called the dump, literally, right? It's either the exhaust or the sink, like think like a drain, or the dump, right? The heat sink, heat dump. This is called the heat source. In this case, it's fire. Doesn't always have to be fire, but obviously fire is very hot. So, right, relative to the air. Here, what's the heat dump? The heat dump is the air, right? Here, the heat dump is the room. So we bring it back to room temperature. So the room right, is the exhaust, the heat sink, right? So we bring it back to 295 Kelvin. That's the ice, right? So the room is the cold thing, fire is the hot thing. So we have heat going in from the fire, dumping out to the room, and that work is now at a higher pressure going out than going in. If we don't dump it, right, the purpose of step four, or steps 4 to 1, right? The heat dump. What's the purpose of that? And again, hopefully you're writing all this down, right? This is like the whole point. This is how thermodynamic cycles work. You can even title it thermodynamic cycle, right? Heat dump, right, brings the pressure down. And if we bring the pressure down, then the work output is, sorry, the work input in the compression is small. So the piston doesn't lose as much energy as much as it gains. So here the piston gains energy because it's all about moving this piston. This is called, guys, ready? All right, pause this if you need to. I'm going to go back to the whiteboard or go to the whiteboard, new whiteboard. This is called a heat engine. Ready? So a heat engine is one that you have heat input and you get net work output. Obviously, there's a total heat, right? Q total, right? Which is, Q in minus Q out or plus, and if you consider Q out negative, you know what I mean? But you kind of get what I'm saying, right? And then you have a work total, which is, of course, the sum of work input, the positive work input, minus the work output. But we already know which is bigger. Well, we already know that for this one, the work output is bigger, and for this one, the Q input is bigger. But what's interesting is that if we add up all of the values, what you'll get is really cool. So if you take like steps 1 to 2, 2 to 3, 3 to 4, and 4 to 1, and you take Q, W, and delta KE for all of them, and you add them up, you get the total. What you'll get is this. And if you go through the numbers, you're going to get that the delta KE is 0. And of course it is. This is amazing that the total change in energy is 0 if you just look at those numbers. And that makes tons of sense because if we end at the same temperature, we ended in the same place, right? We went through this cycle. We went like this, and we end in the same place. We end at 295 Kelvin. And remember, this is delta T, right? This is the temperature, right? Conceptually. So if T is constant or T ends the same, even though we went on a little journey and we had heat and work go on, right? Exchange of energy, ultimately we end up in the same state. Those particles aren't moving any faster or slower. So it's the same. Awesome. That makes sense. But what's really interesting is this, and if this is the case, by the first law of thermodynamics, you should get that this is positive, sorry, 689.4264 joules. That's what I get. 689.4264 joules. And if you do the work values, which at first don't, they just kind of seem like random numbers. They're like, okay, cool, that's a number, great, it probably makes sense. But if you add them up, remember, that's for this step, work input, and this step, work output. And this is the positive Q over here. And here's the negative Q over here. We have our little diagram over here, right? Kind of helping us. We have more positive Q than negative Q. Cool. We have more negative work than positive work. Cool. Well, of course they're going to match because heat input has to be the same as work output. So if we add up those numbers, we get the same thing. Well, what? We have ourselves a heat engine. Dude, that's so cool. That's so cool to me. I just think it's amazing. The numbers end up like being this perfect like symmetry of you have this fire and it pushes on a piston and then reducing the pressure back to atmosphere and then compressing it at a low pressure. Remember, compressing at a low pressure allows you to then expand it at a high pressure, so you get mechanical advantage. You're converting heat input into work output. This is called a heat engine. Boom. Pause this. Hopefully it makes sense. You can go and confirm the numbers on your own. I encourage you to, but at least understand this concept and how we derived this from looking at each step individually. Now what we're going to do is look at it as a whole. So we can do a few things. So a heat engine is this, right? We can do two things. We can first draw the PV diagram for a general heat engine. Any heat engine has a low compression, a heating, and then a high expansion, and then a cooling, right? It doesn't have to be a box. It doesn't have to be four individual steps, but it has to have those elements, which means it makes a clockwise either circle, square, rectangle, or this like weird adiabatic isochoric shape. It doesn't matter. But do you see the pattern? What do we have here? We have work input, low pressure. And then we have work output, high pressure. How did we get the pressure high? We heated it. Q input, right, to increase the pressure. And then we have Q output to decrease the pressure, such that when we compress it, again, it's at low pressure. Hopefully, I'm repeating this enough that this makes tons of sense. Isn't this cool? So any clockwise, you can make up any shape you want, right? Any clockwise shape is a heat engine because you're compressing it at a lower pressure than you're expanding it, and the heat causes that to happen. And so you're dumping the heat here so that the low pressure allows you to compress it at a higher pressure, or sorry, expand it at a higher pressure. Whoa. That's it. Yeah. So how do we draw this also? You can say I have heat input, right? And then lesser heat output. And some of that is put into work output. So I know that there's also some like what is it? Work input as well, right? But I think we can just look at it like this. So the work output divided by the heat input is what's called the efficiency of the engine. And if you're starting to understand that, then you're now taking it to stage four, which is looking at heat engines now from an abstract perspective of what we're doing is converting heat, which is, remember, what's heat? Heat is like particles colliding, passive, right? Right? Hot, and then maybe that's the cold one, maybe this is the hot one. Boom, 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 boom. And then so we have heat going in here, which raises the pressure, which then pushes out on some piston with some force, right? Work output. So we have heat input causing mechanical work output. That's kind of cool. So do you have the obvious two questions? What are the obvious two questions? Did you find them? Ready? Obvious two questions. Obvious question the first. Can an engine, maybe you have another cool question, but these to me are the two obvious ones that come kind of naturally. Can an engine be, not that kind of bee, don't do it. Oh, engine bee. I just thought of the consciousness of bees. That was crazy. I imagine them buzzing around going like, this feels good, this feels good, this feels good. Zzz. It's the thermodynamics of a bee. That's crazy. I digress. Can an engine be 100% efficient? Meaning, can you convert heat entirely into work? What does that mean? That means you need no work input and you need no, right? Sorry, that's supposed to say equal. heat output, which means you entirely convert heat into work. Instantly, you see that's impossible. And what we get is that the maximum efficiency is something we'll talk about later, right? This is the Greek letter eta, is 1 minus the ratio of the temperature of the hot to the cold source. Oh, wait, sorry, cold to hot. Yep, I had that backwards. Of course, hot to cold would be greater than 1, right? That doesn't work, which is kind of cool. So if the cold is colder and the hot is hotter, you have greater efficiency. And that should make sense. If your fire's hotter and you have it be colder, what this is like is kind of like a water wheel, right? So you have like water, like a waterfall, and you have some height, right? You have height initial, right? And height final. Or should I say y initial, y final, because we know better, right? Those are our coordinate systems. We learned that from springs, right? Y initial, y final, and obviously the delta PE is going to be mg, right? Delta y. If you have a greater delta y, right, you have more energy converting, right, this water wheel into that. So this was originally figured out by a French physicist named Sadi Carnot. This is called the Carnot efficiency. And I'll talk about the Carnot engine that has this efficiency, right? Right? That no engine can be 100% efficient because you need a compression. Obviously, you need to make the volume small to expand it. You can't physically keep expanding a volume. I'm going to say that in words. I'm not going to write that down. You need to physically keep expanding a volume, which means you need compression, right? For expansion. You need to make something small before you can make it big again, and you can't make the pressure zero, and the pressure is never equal to zero. But if you get to absolute zero here, if Tc is zero, then the pressure is zero, then you have 100% efficient. So if you had an absolute zero heat dump, you could get a maximum efficiency of 100%. Boom. It turns out that's impossible because everything's always moving. You can't get to absolute zero because as soon as you touch it, it's not absolute zero anymore, right? There's no isolated system in the universe. That's actually the third law of thermodynamics. Isn't that kind of crazy? Ah, isn't this cool? This is so cool, right? So these make a greater efficiency because you need the compression for expansion, and of course you need the dump, the heat exhaust, to lower the pressure, right? You can't get work output unless you compress it, and you can't compress it unless you have a low pressure, otherwise you're going to lose energy. So you need each step of the cycle. I hope those words make sense. Rewind that if you need to, because I think that came out clearly. It's kind of like a water wheel, right? Right? You need this height, right? The water had to come up somehow for it to go back down, right? The water was brought up and it needs to come back down. I don't know if the water wheel helps. Forget it if it doesn't make any sense. Maybe the thermodynamics on its own makes sense. So that's the answer to that question. We'll go into the Carnot engine later, but I hope this made a hunt like this whole point we got from our previous diagram. The second obvious question, which I forgot right now, what was I looking at? Oh, what's the second question? I remember. The second obvious question is this. Ready? So if a heat engine, right? Ready for this? Is heat input into work output. And I have this heat, right? I was just drawing this diagram on the previous page, right? This diagram right here. Wait, sorry, the previous one, right? This one. Heat being converted, right, into work, right? Like this. What if I turned these arrows around? What if I made it so I actually had work input and converted it into heat output? Like I push a piston and it forces heat, right, to go from here to here. thus making this colder. So heat leaves this gas. I push on it, which might make it hotter temporarily, but then it ends up making heat go this way. Hmm. And so then this gets colder. This is called a heat pump, otherwise known as a refrigerator. What do you think that looks like on a PV diagram? Well, that looks like the arrows go the opposite direction. So here I have my, right, heat input here. I have my heat output here, right? And I have my work output here and my work input here. If you figure this out, what you're going to get, that these are the biggest, just like in the other, and your work input, the compression, what it does is it forces the heat output to be bigger than the heat input. Now, this one's a little less intuitive, but I just wanted to point out that you can literally turn these arrows around in the diagram and turn these arrows around like in your mechanism almost, although you do have to design it differently. And you can literally force heat out of something. And this is how your air conditioner works. Isn't that crazy? We'll go over that later, either in like personal project or in class or in a future video. I don't know. Something like that. Isn't that beautiful? All right, that's enough. We did it. I hope that was informational, interesting, and all the good stuff. I'll see you guys later.